I'm really sorry that I was late. I didn't expect. I left my hotel at 8:30, and I got an Uber at 8:40, and the traffic and things, and then the Uber actually took me to a wrong place. So I had to get up that wrong place, and I had to wait for another new Uber. And then a new Uber actually put me on the way up down there, right on the entrance, and I don't know where to go. And luckily, I actually met a Taiwanese student, graduate student from computer science, and he willing to take me to here. So finally, we got here. We late. I think it's okay. We have 5 days, so we can compensate the time. Again, really, my apologize for being here late. So tomorrow I'm gonna leave very early, so make sure. And I now know I know the place, so I don't think that we're gonna be late again tomorrow. Okay, so again, I'm really sorry about that. So are you sure that the audio on the recording and is okay, right? Everything is good. Can I start? Good. I can start. Okay, perfect. Okay, so this is gonna be the mix between, slides and writing on my iPad. I actually, because we record, so I'm not gonna write on the blackboard. We're gonna do an iPad as well. Okay, so the first part for today, so the first hour is gonna be about what machine learning in general, right? To give you an idea what machine learning is, what is the difference between machine learning and a traditional learning, right, or traditional programming, and what type of methods, and why machine learning is important. But we're gonna focus on deep learning for this short course, right? Okay, so that's basically what I just said to you. So we're going to learn about some of the important techniques, in particular deep learning, right? And then we're going to see there's many approaches. We're going to learn only one, which is supervised learning, right? The reason is that our time is limited, but I hope that is actually provide you as the base or a stepping stone for you to actually to learn the other machine learning technique if you wish. Okay, so that's the idea. So what is machine learning about, right? So actually we use machine learning every day that we actually are users, and some of us are researchers, right? But most of us are user, right? If you do Google search or any search out there, you see that as soon as you type Google and it's automatically fill up and then give you options. This is machine learning, right? Behind the scene is actually a natural language processing to predict the next word, right? That you're gonna type. So that is the and transformer, which technique transformer is a specific technique in deep learning, right? But we're not gonna talk about that. But most of these actually empowered by transformer, but we're not gonna talk about that. So when you actually use your phone, right? You're asking a lot of things about this is your phone thing, right? So behind the scene again, speech recognitions, questioning, answering, right? Assistant behind the scene is a machine learning. Um, Spam. Everybody had to deal with spam. Right? We had to delete email all the time, and instead of delete, you actually mark which one is actually spam email, right? And then over time, a few time over time depends on your uh, um, um, mail application. They're gonna learn very quickly or not, right? So they're gonna detect and they say, oh, this is gonna be spam. In the future, I'm gonna put that into the spam email. So behind the scene is again is a classification and put them into the um, um, spam category. Okay, so another thing is that so this is our future, right? That's the hope. In the U.S., it's actually a big deal, and actually many part of Asia, I think as well, is on autonomous vehicles. So we already have autonomous UAV, autonomous vehicles, sorry, unmanned vehicles, right, for military purposes. But autonomous vehicle for humans is actually a little bit more complicated, right? Because safety and all of the other, issues, security and so on and so forth, that actually harder. So in the U.S., there are a couple of cities that actually allow, autonomous vehicle, right? And the particular taxi, like for example, Phoenix. But still, it's not very popular. So the reason is that people are so scared, right? With the autonomous, we're not gonna know what's gonna happen. It's gonna, can hit people, right? Because as you know later, when you learn machine learning, this class will not offer that, but machine learning is wonderful and great, right? But it can make mistake, right? And the mistake in this type of application can lead to death, which we not, as a human, we are very scared about that, right? We freaked out and said, no, we're not gonna use it. Okay, so this is the autonomous again. This is about object recognition classification. We're gonna talk about that a little bit later. Um, okay, so this is actually if you add to this class, right, the whole thing, the week, this actually perhaps one of the most important slides, right? Because this is actually where we understand what machine learning and traditional programming, right? This is the key. So traditional programming is what? You provide input and rules, right? So can I write on the whiteboard as well or no? Yeah, so but yeah, let me see. Okay, so actually maybe I should talk, right? Writing maybe is a little bit better. How about writing and talk at the same time? And so you can, the person on the recording also hear it, right? So for the traditional programming, let's say I want to do the plus function, right? I want to do the plus functions. So the input going to be x and y. I'm just adding two numbers, right? And then this is a function, right? This is our function. Let me say, I don't know what language that you use, but I just do a generic here. This is a function. This function output is the sum, right? Let's say. So these functions, when you provide input x and y, and then it add like actually no, let's do x1, x2, and then it's actually inside, right? We're gonna return x1 plus x2, right? This is traditional programming where you know the rules, right? You just have input, and then you in the traditional programming, right? You actually put input and rules. This is the rules, right? Plus is the rule, and then the answer is actually just the sum, right? That's a traditional programming that we have been doing, right? All of us are doing. What is machine learning here? The input of machine learning is interesting, right? Because you also not rule. You don't the machine learning programming actually you don't input the rule, but you actually input the answers, right? So what you actually do here is that you don't input the rule, but you input the answer. So what it does is that let's say, right, you have pair of x1, x2, I, and then you have the sum, right? Sum, let me call it sum I. So you say, for example, x11, x21 is 1, and then the sum one would be 2, right? This if x12 is 2, x22 is 3, then sum 2 gonna be 5, right? So you input the input, but you also you actually provide the results of your task, right? And then machine learning after those, right? Those is when we say machine learning here behind the scene, we're gonna talk about the more technical terminology is actually learning training, right? So we're gonna train the machine learning techniques, right, based on both input and the answer. And what we return is actually we return the rules. In this case, we try to learn the rules, right? So this is hopefully after you train, you learn the blood functions. Okay, so this is the difference between traditional programming and machine learning, right? Let me repeat. This is very important because if you talk about machine learning, this is the key that we need to distinguish between traditional, right? So for the traditional approach, you put input and you put rules, rules, right? And then you actually apply that rule. When the rule see the input, you apply the rule and then you return. For the machine learnings, you don't input rules because you don't know, right? You don't know the rules, but you know those samples, right? And sample. I'm going to talk about that later because machine learning in general is very like human, like us, right? Let's think about kids. If you have a young child, or we used to be a little one, right? So our parents say, okay, this is a cat. So you see that if an animal have four legs and with that shape is a cat. So the output is cat, and that is the animals, right? Oh, whenever you see that thing, that is snake. So we actually human learn by actually machine learning ways because we learn that we have the input we have an answer and we try to learn the rule. That's actually how we operate, right? So machine learning trying to do similar, right? When you see the stop sign, oh, that's the stop sign. Oh, this is the U sign, right? Oh, that is human, that is animals, right? This is an SUV, this is a truck. So we learn by example, and we learn by having the input and the output or the answers. Okay, and then we try to learn the rule. That's the key. Please, actually the most important thing that I want you to have for this first hours, which, not first hour, right? Again, don't worry, we can make up the time later. Okay, so this is just to show you a case why you said, why don't we do without rules? Why do we need to do that machine learning, right? Why do you actually have the input? Why do we have an answer, and then you try to learn the rules? Why do we do that, right? Think about the autonomous vehicles again, right? Self-driving car again. If you do rules, that's fine, right? That's fine. When you see this person, that's actually you see that this is a rule. Just an example here, by the way. This is Python, right? Code snippets just for demonstrations. So let's say if it's a four-wheel, then it's a car. Two-wheel, then it's a bicycle, right? Or depending, look at the back or at the front. You see that? That's complicated. And if you want to do the rules, you see how many if and else that you can do? You will never can do if else for everything in this world. You see that, right? You can claim that I want to do rule, but unfortunately we have so many objects. Basically, we could have countable but infinite number of objects that we need our car to detect. But unfortunately, that's too much for programming. So this is actually become infeasible, right? It could be possible. So that's why that's where machine learning come into the pictures. So machine learning approach, like I mentioned to you, we learn by examples, right? So we actually look at detections by given. You see that, you guys, right? This is, I'm sorry. Huh, where I am? I'm sorry. Oh, okay. I'm sorry. I'm sorry. I wrote the wrong. Okay. You see that? So you have to detect which one is vehicle, right? So machine learning say, oh, this is vehicle, right? This is vehicle, this is vehicle, this is pedestrians, right? This is a vehicle action, right? And then this is a block. By looking at these examples. So what we do in machine learning, and in particular, this is actually supervised, right? Where you provide input and you provide the answers, right? That is supervised because you know label which, oh, this is snake, this is cat, right? Then these are supervised learning because you know the answer first. Okay, so in this supervised learning, there are three steps, right? We first collect on a data set, right, with the training sample. For example, if the shape look this way, right, that's a vehicle, right? If a shape look this way, this is a vehicle. So that's we put into a training samples, right? Just a collection of all data, and then right, to output accurate prediction on this data set. Of course, right? We need to actually do well on the data set. But on the most important thing is that now in the future, when you have a new but similar data, right? Then our models, or now we have we only learn the rule, right? After we do this, after we train with the current samples, right? We learn the rules. In the future, you just need to provide X1 or X2, right? Now machine learning immediately actually return you the sum, right? Hopefully, right? Okay, so that's the supervised learning. So the example is in there. You by the way, this is a scikit-learn. If you notice here, scikit-learn software, but we'll talk about JAX later. But this is just I use scikit-learn to teach the class, but JAX I'm actually transition to JAX right now. So I'll talk a little bit about JAX later for with you as well. But this is a scikit-learn example, okay? The beauty of scikit-learn is that it's actually have a lot of machine learning lab, program or model already implement, right? It has a lot of data sets in there, a lot of things that's already available for you to use. Okay, so I'm gonna skip this. So this is basically the Boston how predictions by learning by examples. Okay, so that we're gonna come back later. Okay, So we actually gonna go through that quickly. We don't need to go. So what is the application? Remember, this is the first part. I'm gonna do very quick introductions. Um, so what is the application of supervised learning? Actually, almost a lot of things that we do in practice, right? Or we use classified medical images, for example, right? This is just a few translation between pair of languages. In fact, that's what I use. When I come to Taiwan, actually, I have to use Google Translate, right? So when I actually scan, or actually I type in the English, or I scan the Chinese or Mandarin words, it's actually translated into the English, right? So that's supervised learning, because every pair, right? We only have pair, one Mandarin, one English, one Mandarin, one English. So now, what in the future, after it learned the rules, now I give a new Mandarin word, is actually give me the English word, right? Detecting object in a self-driving car, right? By based on previous example, oh, that is a pedestrian, that is a car, right? Or that is a stop signs, or that is the walkway, that is a traffic line, right? Based on these examples, it's actually now in the future, it's going to see something similar, it know what it is. So that's supervised learning. So that's the first learning techniques. Okay, that's actually very important one, right? Actually, there's only three, but you can do more. I'm gonna talk about that a little bit in a second. The second important machine learning techniques is so-called unsupervised learning. So I'm gonna finish as a couple of more minutes, right? We're gonna return to this, and so that we can have 5 or 7 minutes break for you. So unsupervised learning, right? Unlike the supervised learning, where x, y, right? X1, x2, right? And you know the sum. For unsupervised learning, you don't know the sum. You just have a whole bunch of images thinking about, right? You have a whole bunch of images of animals, a whole bunch of images of car, a whole bunch of images of humans, and we never say, "No, that is human," or that is a female, or that is a male. We never say anything, right? We don't actually, we don't provide the label, right, or the output. So unsupervised learning is a class of machine learning, right, based on the data set, try to figure out the rules, right? In particular, try to find, cluster hidden in the data sets, right? So if an unsupervised learning method, if a good machine learning method, right, unsupervised learning in particular, if I give them, a set of animals, figures, right, or images, and then a set of human images, and then a set of car images, right? That's unsupervised learning. Whatever it pick, it should be able to clusters on the animal into one category, and it clusters on the human in another cluster, and help, and then cluster on the others vehicle into one cluster, right? So it's based on the unlabeled data, figure out the relationship, right, or the hidden structure in the data. So that's the is unsupervised learning, one of the example. Another one is outlier, right? And so, for example, right, all the data set that you have is images of human. One of them is actually animals, right? It should be able to detect, if a good unsupervised learning should be able to actually figure out one big cluster of everything, and then one little cluster, right? Or one cluster that have only one point, which is an animal, right? So that is important as well. And then this is actually very useful. The third one is actually very useful, right? When you have cell phone every day, you talk on the street, right? It's very noisy, and amazingly, on the other side of the line, actually can listen to you well, right? You never have you ever actually pay attention to that? Even in the crowded people, talking very loud, when you talk to somebody, they still can hear you, right? The reason is that behind the scenes, right, unsupervised learning techniques filter out the noise. Which one is noise, right? Which one is actually your voice, and actually filter out. Right. So on the other side, you can still have the noise, but it's actually very, very small, right? Compared to what saying, for example, right? You make some move there. I talk here in the record video. It should be able to make that, not a movement a little bit very tiny, right? Okay, so that is another important class of machine learning. This is only like three, example, right? But it can be many, many more. Okay, so I'm gonna actually go through. This is just example. We're not gonna go through that, but there's a code in there, right? Uh, Last one. Don't worry, I'm gonna let you have a 10 minutes break, and when let me finish this, okay? So the third one is reinforced learning. This is actually a very important class of machine learning as well. So we have supervised learning, we have unsupervised, and the third one is reinforced learning, right? What is it? This is actually what we do every day, right? Like me today, that might I make mistake, right? I look at the weather. Last night or this morning I checked Google Map, right? It take me 50 minutes to get here from where I stay in Taoyuan, right? So I went out by 8:30. So you see that in this kind of reinforced learning, we have environment. So in this case, the environment is on, the traffic, on the situation in Taiwan, right? And I make a decision. I make a decisions. I take actions. So the state, right? So that's where I am. I was in Taoyuan, right, at 8:30. So that's the state where I am, right? And the environment, which is, the whole traffic situations, right, in Taiwan. And then I make a decision, take action. Okay, I have enough time. 1.5 hour should be more than enough, right? So I said, okay, I book Uber at 8:30. That's my actions. I take that the one, right? And then when I book Uber, I get even the reward here. Actually, the reward here should be in code, right? It's just a nice name, reward. But report can be negative or positive. For me, my reward this time is actually negative, right? Because I was late, right? Um, so then I move here, right? I move here, and then the new state is that our class was late, right? So then I have to make another. Now the environment is that our class was more than 30 minutes late, and the environment is that we are in this environment. Everybody was waiting for me, tired. So I have to make a new decision, right? Decision, right? So then I have to skip on example, for example, right? I didn't go into example because not necessary unless we have time. So, and then that's what we do, right? So you do the same thing every day. You step out your door, you look at environment, you make decisions, right? And it change the way the environment and you, and then you make decisions. If you do stock, especially for those who do stock, right? You the same thing, right? You look at the stock market, you make a decision, buy or sell, right? And then either you get reward, which is you get some money, or negative reward, you lose money. And then again, you have a new environment, and then you make a decision. That's how it does, right? Again and again. And this is actually very important for us, right? If you look at the Google Map, I mean, because I'm from US, right? You Google Map all the time, it can tell me the environment where the traffic are and so on and so forth, right? And it help me to make decisions. So this is actually very important. For example, another important is that where we are in Taiwan right now, right? Maybe I can say this. Where should I put the Air Force base or whatever, right? Military base to protect the country from the others country. For example, right? Where should I put them? How much? Where should I put them, and what action that I should take, right, to protect the country, for example, right? So there's that. Just so this reinforcement is really really important, right? Of course, every example there is every supervised learning, unsupervised learning are equally important, right? But this is one is actually exceptional important as well. Face recognition, actually, the another supervised learning is face recognition that I didn't tell you, right? When actually I travel here from US, when I go to the airport, check in the boarding, right, on the plane, it actually it's only take a picture of me. Didn't do anything. I didn't even need to show my boarding pass. So I stand it. I took United Airlines. So I just take a picture. I just stand on the camera. I took a picture of me. Exactly know who I am and where I sit on the airplane, right? That's a supervised learning again, right? Face recognitions. And face recognition is also very important. Okay, so these are three class of application of reinforced learning, right? Let me actually, another reinforced learning is here. I'm sorry, I sneak in the supervised learning, but let me actually finish this reinforced learning. So chess game, Go game, right? These behind the scenes actually reinforced learning, right? If you play these with on the machine, right, the machine was trained by reinforced learning. design new drug compound. I mean, these are not things that I know. Okay, I think this is another the important slide that I like to mention at the last slide today is this slides. So artificial intelligence is a large class, right? Large class of like using think this is a bigger set of learning or artificial intelligence. Machine learning is a subset of artificial intelligence. And deep learning is, in particular is even a smaller set, right? Is a subset. So this is the Venn diagram that I want you to have in mind because we mostly going to focus on here, deep learning, right? We're going to focus on the small subset of artificial and machine learning. Okay, so that is our plan. Okay, so let's take a break for you know 8 minutes. We're gonna see it again, each other again at 10, 10. Okay, let's take a break. All right, so welcome back. We're gonna next to the next part. So let me, before we start, how many of us have taken optimization class before? Can you raise your hand if you took optimization class before? So don't be shy. Don't be shy. So yeah, we have a few. Yeah, we have a few. Okay, good. We have a few. So yeah, we're gonna do because for the supervised learning, or either you do unsupervised learning, you still do optimization, right? Most of the machine learning method behind the scene, the workhorse, optimization. So let us just go through optimization very quickly so that all of us are on the same page, especially for those who haven't seen. And let me ask another question. How many of you are from math department? Okay, so most, okay, good. So perhaps, how many of you actually come from non-math department? A couple, okay, good. Okay, so that I know what to do, right? Okay, sounds good. So we're gonna cover the important idea about optimization, particularly. So this is just the broad. Okay, let me actually write it. So so topics today. So our topic we're gonna cover. So unconstrained optimizations. In particular, I'm going to go down to the first order optimality condition. How many of you are undergrad? Are there undergrad student here? Oh, okay, good. Um, okay, and then we actually look at the we're going to derive the gradient or gradient descent methods. Because this is actually right the main workhorse in machine learning, gradient descent. And then third, we're going to do conversions, right? Conversions of gradient descent. So that's what we hope for, right? I don't think we're gonna finish in 1 hour for this. Maybe we need 2 hours, which is fine. We're gonna go over that in the afternoon as well. And then the next one we talk about probability, right? Again, probability is another important subject for machine learning. We have to know basic background in order to talk about machine learning, in particular deep learning. Okay, so that is the plan for us for today. I'm going to start first with unconstrained optimizations. We're going to consider, right? First, we're going to do one-dimensional optimizations very quickly. And in fact, this is the key. Because you actually can derive, you understand the one-dimensional optimizations, you can do optimization derived for every, right, in finite high dimension and infinite dimensional setting. Okay, so so we're gonna start with one-dimensional optimization. Our object, right, here functions that take R and return a number, real number, right? R to R, real to real. So that's the function. And if you give this an x, it's going to return an fx, right? That's the setting. And I'm going to do some of few a little definition here, definitions. Ball. Okay, so we write B as a ball with the radius epsilon around some x star, right? This is ball with radius, ball with radius epsilon, center at x star. Okay, so what does it mean? It means that this is the collection of on x such that x minus x star is less than epsilon. Okay, and this is actually open ball that we look at. Okay, open ball means that if we have equal sign here, right, it's a closed ball, but we're gonna look at open ball. Okay, so that's the first things, and then we look at the next thing is the definitions of an optimizer, right, or local optimizer. So what we're gonna define here is that is the following. So x star is called a. So we implicitly, right? We're not gonna repeat. We're not gonna repeat that is local. Okay, we're gonna implicitly understood that everything we talk here in this lecture is a local. So we're not gonna repeat local anymore. Okay, so X star is called an optimizers of f our functions if there exists there exists there exists an epsilon greater than 0, right, such that f x star is less than or equal to f of x for all x in the ball of radius epsilon around center at x star. Okay, so basically what it means, right? What it say is this: if x star is local minimizers, then right locally, right? So if I am a local minimizer, then locally I'm the lowest point. Everybody see that? That's intuitively what it means, right? If I look locally around me, then I'm the lowest point. That's basically what it is. Or equivalently, right? We also write. So or we write that x star is equal to r min minimization of f x in r in our case here. Then or if we want to precise, then we just for all x in the ball center as x star radius epsilon, x star is the lowest point. Okay, so okay, so sometimes f is called objective functions. Sometimes it's called cost functions. Different field called differently. And machine learning, we don't call this, right? And we do machine learning, we call loss functions. Okay, so when we talk about loss function, we mean this, right? A function where we want to minimize something called a loss function. And I'm gonna tell you later why the name lost, right? Why do we call it loss function? So there's an intuitive meaning later. Okay, so that's good, right? So the first one is the if, right? The question that we want to ask ourselves questions. If f is differentiable, if f is differentiable, right? and x star is a minimizer or an optimizer right? We use both of them interchangeably, optimizers, and x star is an optimizers. Then what can we say? Sorry, can we make this a little bit taller? Do you think it's higher? I'm sorry. Can we make it a little bit higher, do you think? I think it should be, right? Yeah. I think I bend so much that I cannot write well. So, yeah. So then it's an optimizer. Then what can we say about the first derivative, right? df dx evaluated x star. We actually also write f prime x star and and the second derivative of f with respect to x at x star, right? Sometimes we write f double prime of x star, or we can write as a Hessian, right? Hessians at x star, or we can write h x star. Depends. We're gonna make it so clear. So what can we say about these, right? So the first theorem that we're gonna cover today, I do some proof, right? And then I ask you also to do something about this. So before I start, can I ask somebody, can you remind me, especially those who take optimization class before, what can we say about the first derivative? If x star is a minimizer, this is zero. That's good. How about the second derivative? Oh, that's perfect. That's good. That's good. That's good. Yeah, that's good. Very good. Oh, and then and move up and down. All right, perfect. Perfect. Okay, that's nice. That's nice. Okay, how about the second derivative? If x star is a minimizer, then what can we say about the second derivative at x star? Huh? But positive, definite. Okay. Yes. So I think it's very good. Thank you. So that's that we're gonna try to say, right? So necessary conditions. Okay. So we're gonna do this, right? We're gonna suppose that f from R to R is twice, right? Two times differentiable, differentiable. Suppose that is the case. Then if f at tens is minimum, at x star, then even then two things that we can say. First, like some of you still remember, f prime at x star must be equal to zero, right? So this is the first order optimality conditions. City known as, or we're gonna call this, right, in this class, the first order. Okay, that's the first order optimality conditions. The second one is like some of you already said, right? Remind us, f of x star need to be non-negative, right? We don't know whether it's non-negative. And this is so-called the second order optimality condition, second order optimality conditions. Okay, so we have first order optimality conditions, we have second order optimality conditions. Okay, so we're gonna do a quick proof for actually very easy, right? So I really want to see you, right? You don't need to memorize. Actually, it's very easy to show both of these, right? So this is just for fun. We're gonna show one of them, right? So we're gonna we do first we prove. And of course, by the way, I'm gonna send the lecture notes to you as well. So I have a type lecture notes type, right? So you can look more details on the other thing. So we're gonna cover part of the lecture notes. So the proof, we're gonna prove one, prove only the first one condition, and we proceed by contradiction, okay? By contradictions. So we proceed this by contradictions. Okay, so before we do by contradiction, we recall, right? We recall the Taylor, right? We call the Taylor remainder theorem. So we learn, calculus a lot, right? Especially Taylor series a lot, or Taylor expansion a lot. This is where you do, right? So when we, especially optimization, we talk and local optimizations. Then on most of the proven other thing is about Taylor expansions, okay? And Taylor expansion is the key remainder theorem. So if I have an fx, right, I'm interested in fx star, right? But I want to move a little bit away from fx star by an epsilon, right? So I know that if I move a little bit away from fx star, then it's going to be equal to fx plus epsilon f prime x star plus epsilon square over 2 f double prime x star plus theta epsilon for some theta less than 0, greater than 0, less than 1. So this is actually equality. By the way, everybody, this is equality, right? It's not approximations, because if you don't have this, right, then of course you have more terms. Okay, if you don't have this, then it become f double prime of star, then you have more things. But the Taylor remainder theorems, you can remove, right? You can replace everything here by f double prime. But the price that we have to pay here is that you don't evaluate f double prime f prime at x star plus theta epsilon. Okay, so and theta, you see that the price that we have to pay by removing the whole series by one single form. We actually don't know what theta is. We just know that there is some theta between 0 and 1 such that this is equal, right? And that's all we need for ours of our proof. And it's also natural, right? You see that it's also natural. Why Taylor remember? This is constructive, in a sense, constructive proof. Why? Because you see that the condition is about the two derivative, the first and second derivative, right? What can we think about the first, second derivative? Where does it appear? Taylor expansions up to second order term, right? So it's also very, very easy to understand why we need Taylor, because Taylor involve both of the subject that we are interested in, right? F prime and up double prime. Okay, so we actually consider two cases, right? Consider two cases. So A is gonna suppose that f prime at x star is less than 0. Okay, then if we suppose this way, then if we pick sufficiently small, right? Sufficiently small. epsilon. In particular, what is epsilon? In the lecture notes, you see the derivation I show you. It's easy, but we're not going to spend time doing this, right? Because this class is not about optimization. This is a quick introductions for you to get everybody on the same ground. In particular, if you choose epsilon less than minus of 2 of f prime x star over m, okay? So so for m is the where, you know, m is numbers, right? Okay, see the lecture notes. Given as. So m in fact, right? M is in fact in fact the supremum, the largest values of the second derivative. Okay, the second derivative of fx over a little bit of neighborhood of sorry, and x is in the x star minus epsilon and then x star plus epsilon. Okay, so if you are interested in detail, but what I'm saying is that, okay, this is a little bit more detail, but you want to see we don't even need that detail, okay? Then that's sufficiently small of epsilon such that epsilon f prime x star plus epsilon squared over 2 of f double prime of x star plus theta epsilon less than 0. Why is that? Of course, if you substitute this inside, that is true. This is just mathematical justification. See more detail in lecture notes. I'm going to ask your professor to send it to you later. But why, right? Just intuition. Why this is true? Why, when epsilon is sufficiently small, then this is less than 0? Can somebody tell me why? Why just by intuitions? That if I choose epsilon very small, and I'm sure, right? You remember that our Taylor expansions there. Then if I choose epsilon sufficiently small, then this is less than 1. That's less than 0. Why is that? Because you see that, I'm sorry, I'm going to show you the flow, right? If I can show that this is less than 0, the last two terms are less than 0, then f of x star plus epsilon is equal to f x star plus something that less than 0. Therefore, it must be less than f x star. Everybody see that? If the last two term is less than 0, then the right-hand side is less than fx star, right? Because fx star minus something will call less than fx star, and that's a contradiction. Because fx star is supposed to be the smallest, right? Remember that if x star is a minimizer, then it needs to be lowest. But then we show that no, I can find x star plus epsilon such that fx star plus epsilon less than fx star. That's a contradiction, right? So that's what we're trying to head into. Okay, so we're trying to show the last two terms less than 0, then therefore contradictions. Okay, then back here again. Why is this? Why epsilon, when epsilon very small, then we know that this is less than 0. Just intuition. So if epsilon, let me say, right, if epsilon is 10 to the negative 8, if epsilon is a 10 to a negative 8, this epsilon is this, then what is epsilon squared? 10 to a negative 16, right? Very small. Just a hint. That's so trivial that you don't want to say. You see that the second term, this one, is very small compared to this one. Everybody see that? Because know that when epsilon is very small, this is even much smaller. This one, right? So regardless, we don't care even about the sign of this one, right? Remember that we suppose that f prime star x star is less than 0. This one is less than 0. and then multiply by a positive and a small number. So this is still negative, right? Everybody's okay with this? This is still negative. And this one, regardless, it's negative or positive. It's much, much smaller than this, right? When I choose epsilon very small, in particular, if you choose like this, right? But now intuition, right? When epsilon very small, this is negligible compared to this one. And this one is positive, sometimes negative. Therefore, the sum is less than zero. Everybody see that? Just intuitions. We don't, right? But if you want to see the little math, easy, very easy. Just in the lecture note, you're gonna see that. Okay, so just by intuition, we see that. So we can only find a very small epsilon such that this is less than zero, and therefore, right? Therefore, f of x star plus epsilon, right, is less than f of x star. Are contradictions. Everybody see that? Because, like I said, right, the last two term is small. Maybe let me write a little bit more, okay? We let me do a little bit more details, especially we have undergrad student here. So let me do this. Or, for those who haven't taken the optimization class before, if you haven't seen this, just copy and put it here. And I'm gonna do the this color. So this is our Taylor expansion, and this one, right? We have shown that this one is actually when epsilon is sufficiently small, and this one is actually less than zero. Okay, so fx star plus something less than zero, therefore must be less than f of x star, right? The right hand side. Everybody okay with that? And therefore this is a contradictions, Very easy, everybody, very easy, right? It's just elementary mathematics here, not even difficult. Okay, any question? Don't be shy, okay? I know that, by the way, I'm a Vietnamese. I grew up in Vietnam, and I went to US 20 years ago. I know that, Asian culture, we typically very shy. I remember when I was a student like you, when a foreigner came and to give a lecture, everybody just, never say anything. Uh, so don't feel that. At least you see that I'm at least an Asian, right, like you. So most of you. um, so you don't feel anything, right? Just if you have question, please raise your hand. Any question is appreciated. Don't worry. Question is not good or question is simple or you worry that your question is just silly, right? No question is silly. Please ask if you're not clear because this in a sense, right? We try to understand machine learning from mathematical point of view. And if you miss one point, you miss the rest, right? Most of you mathematician or student here, if you miss one point in a lecture, you may miss the rest of the lectures, okay? So raise your hand if you don't get it, anything or anything that you want to clarify. Okay, so I'm gonna ask you to do the homework, okay? You're gonna do the homework. I'm gonna ask you to do two things. And of course, the lecture notes in there, right? So you can check our lecture notes as well. We do a second case, is B, and I'm not going to go through that. I'm going to ask you to do. B is now we'll suppose that, so F prime X star cannot be negative. And we check, oh, how about, is it possible that it's not positive? Okay, again, similar proof, right? Similar proof, similar by contradiction again, right? You can conclude that, no, contradiction again. So that's gonna be your homework. Okay, so homework, and then you also can show, right? We can also show show that h or the second derivative of f at x star cannot be negative, right? Cannot be not be negative. Okay, and by contradiction, right? Again, just look at lecture notes. Therefore, we conclude that f double prime x star. Oh, I'm sorry. Actually, I was excited. I should have say one more thing before I move this. Okay, so back to the first order, right? F prime x star cannot be less than 0. F prime x star cannot be greater than 0, right? The only possibility is f prime must be equal to 0. Okay, so therefore we conclude that it is necessary that f prime must be equal to 0. Okay, so done, right? That's we conclude the proof. Similarly, you can show that f double prime cannot be negative, right? And therefore we can conclude f x star must be non-negative. Okay, so that's the end of our proof. Very simple. That's why I want to show you. It's not difficult at all. Okay, so there's a sufficient conditions. It's good to write out sufficient condition as well, but we're not going to prove. Again, I'm asked you to do that as homework. We don't use the sufficient condition in our work. Okay, and I'm going to tell you why we need it later soon. Okay, so the next thing is sufficient conditions. Sufficient conditions is a little bit opposite, right? So we are still suppose that f is twice differentiable. Now we don't assume x star is a minimizer anymore. We're not gonna assume x star is a minimizer anymore. Okay. So the only thing that we know is that if at x star we have the following two conditions. We have f prime is x star is equal to 0, and then actually here's a way that I can ask you to remind, right? Then actually I'm on purpose I do this, right? At x star, if we have this and this, then x star is a local minimizer. So actually there's a mistake here, right? There's actually something wrong here. One little thing that's wrong here. Can somebody tell me if you know what's wrong here? So suppose f is twice differentiable, and suppose also that at x star we have the first derivative is equal to 0, the second derivative is non-negative. Then x star is a local minimizer. What's wrong about it? It's almost correct, especially for those who took my optimization class before. What is wrong here? Oh, yes, please. You raise your hand, right? Did you roll your hand? Okay. What's wrong here? Something very small that actually need to be corrected. Yes, please. Borderline. Oh, yeah. No, no. We assume that unconstrained, so there's no constraints, right? So we assume that the domain is R, so there's no constraint here. But it's good suggestions. What's wrong here? Huh? The inequality, which one? The second one. So what do you want to change it? That's correct. That's correct. Everybody, that's good. That's great. So don't be shy. I know that, you know. Yeah, so you see, this is the positive, okay? Need to be this and positive in order for X star to be a local minimizer. So that's a sufficient condition. If you have these two, then we know for sure. But if you have an equal here, then we're not going to be, we don't know, right? So because if this can be equal, actually it can be a saddle point problem, right? It's actually can be uh, um, um, also can be a maximizer. Okay, so okay, so we're not gonna prove that. I'm gonna ask you to actually do it at home, proof homework. Please check it out, right? Do it yourself. But the reason that we want to raise up the subtraction condition is later when we discuss about gradient descent methods, right? Gradient descent methods, we're gonna see that we don't need this, but we're gonna replace this with something else in order to make sure that when the gradient descent approach, right, you carry out the iteration, it's gonna converge to a minimizers. We're gonna replace this because this one is actually hard to check, right? In general, especially in multi-dimensional setting. Okay, so and then extensions. We're gonna extension to a multi-dimensional setting. And this is really, I mean, the reason I call it is not just, for fun, everybody, like I said. Optimization, gradient descent is the workhorse of machine learning. When you train machine learning model, in particular deep learning, most likely you're going to do gradient descent, right? In fact, we're going to do stochastic gradient descent. We're going to talk, that's why we need to talk about, we need to talk about, probability, right? So that's why we need to prepare today and a little bit tomorrow for us to dive in the deep learning, okay? So multi-dimensional setting, F is now, we just from Rn to R, and see the lecture notes. It turns out, right, turns out that we can use, one-dimensional theory to straightforwardly, right, or to develop, or to develop result for multi-dimensional. So look at the lecture notes, right? So look at the typed lecture notes. So we simply, in fact, we're gonna simply yield the we up here. We simply yield this derivations, right? We use this actually to derive the multi-dimensional setting. Let me just write out here for you, right? So a theorem or a lemma. So necessary condition again. Okay, now I'm gonna ask you again, but let me do this. F from Rn, unconstrained optimization again, Rn, R, right? Twice differentiable. And it take, x, vector x, and return f of x. Okay? And then the conditions that we have is very easy. Okay? So if, it's not easy, if x star now it's a vectors. If a vector x star is a minimizer of f, then it is necessary that first condition. Can somebody remind us what's the first conditions? Remember that, remember that. Okay, so sorry, I have to go up and down a little bit. Sorry about that. Maybe let me copy and put down here for you. That's the best is actually, so this is the beauty of using iPad. So I can copy and then I can erase. Let me copy down here. Let me copy down here and then we erase in a second. Okay, so this is down there in the box here, right? Is a necessary condition. You see that the first statement and this one, the statement is still the same, right? The statement is still the same. But the first condition, what would it be for the multidimensional? The gradient. The gradient must be a 0. That's correct. That's a gradient must be 0. So so by talking about that, I need to actually make some convention for us as well. I'm sorry. We're gonna delay our statement of our theorem in 1 second. We're gonna define a couple of things. Okay, we define that the gradient of f is defined as the derivative of f with respect to x1 dot to the derivative of f to respect to xn. That's what we call as the gradient vectors. And then we also define the Hessians, the Hessian of x at x, which we typically denote as the second derivative of x is defined this. So we do row by row. Okay, so we're gonna see that the gradient is a derivative, partial derivative of x1 with respect to xn, right? So the first row of the Hessian is partial derivative f. We do one more derivative of the first component of the gradients. We do one more partial derivative of the first component of the gradient. So we would have d square f dx1 square. Everybody see that? And then the second one is d square f dx1 dx2, right? And so on and so forth until d square f of dx1 dxn. So that is the partial derivative of the first component of the gradient, which is a vector by itself, right? So we put on the row of a matrix. And we do the same thing for every component of the gradient until the last one, which is now the second derivative of f with respect to dx1, dx and dx1, right? The second derivative of f dx and dx2 dot to d square f of dx n square. Okay, let me do the statement of the necessary conditions, and then we done, right? We're good. Okay, so let's do that. So the gradient must be 0. The gradient vector of f of x star, and it turns out, right? We just need the theory of one-dimensional must be 0 vectors. And then second, the Hessians, which is the second derivative of f of x star, need to be non-negative again, but this one it may be semi-positive definite. It could now become a matrix, right? Semi. Because it's a matrix, right? We should define both. Okay. Okay. So we're gonna see each other at 1 o'clock. Okay. Any question before we go? No. You're quiet. All right. See you at 1 o'clock. Okay, so we continue. So this is a method, right? So I show you the general idea now, pseudo, right? Pseudo idea. We need to have a like a general structure, pseudo idea. What is it? The idea is this, right? So the first step is you are given an initial guess, or you just guess, right? Initial guess, x0, and then you iterate, right? While. So in particular, remember, right? Actually, here's the thing, right? Here's the thing. Remember that you see that either the necessary condition, actually, let me go up there to see better. So either the sufficient conditions or the necessary conditions, both of them have share the same common, which is f prime need to be equal to 0. Okay, so you see that up here again. So f prime need to be equal to 0. So for if x is a minimizer, then f prime x must be 0, right? If x at x fx is 0, and of course f prime x 0, and then of course the second condition, then x is a minimizer. So what I'm going to try to show is that what we try to do is actually try to find a point at which the gradient is actually 0. Okay, so then when I is equal to 0 first, while the gradient of f as xi is, and then you take the norm. Okay, actually I should have to define the norm. See the definition of norm, by the way, I'm sorry, I should have defined, right? The norm of a vector x is for us, right? In this case, that you take on the component, you square, and then you sum I from 1 to n, and then you take the square root, okay? So that's the norm for us. So the gradient is a vector, so this is just the L2 norm, right? Standard L2 norm. So as long as the gradient norm is still greater than some tolerance, some prescribed tolerance. As long as it's still prescribed tolerant, let me call this tau, right? Tau. Then we iterate, right? We update, right? Xi to xi plus 1, and then n wow. Okay, so very simple idea. So you start from some initial guess. If your gradient is still greater than some tolerance that you choose, of course, right, you can never get to 0 exactly, because computer is finite precision. We know that, right? So you iterate, you update somehow, right? So this is the key step that we're gonna do. So and then hopefully we get a better. So we iterate, we get better iterations, and then hopefully we get closer to that, right? So this step is done by this step. This step is done by gradient descent. And by the way, let us put here, right, the main workhorse of machine learning in general, and deep learning the stochastics, a gradient descent. Right, called GD. Okay, so this is our first step. We need to know what gradient descent first, and then we're gonna go through some probability theory, and then we go to stochastic gradient descent later when we see deep learning training. So that's why we need these lectures. Okay, all right. How many of us How many of us know gradient descent method or steepest gradient descent? Some actually call steepest gradient descent same thing. How many of us have seen gradient descent before? 1, 2, 3. A lot. Okay, good. Perfect. My question to you next. Have you wondered how gradient descent come up? Have you taught, were you taught how to derive it? Or you just, oh, this is gradient descent and then just keep it in mind? Okay, so I don't like just, I'm an engineer, I'm a mathematician at the same time, so I'm not, feel comfortable if, we memorize or just given and trust, right? So what we're gonna do next is, and this, you're gonna see, very simple. We're gonna derive gradient descent, why it come up, why gradient descent is good, right? How come one came up with the gradient descent approach, okay? And again, Taylor expansion is the key. Gradient descent is, of course, obviously it have gradient in there, gradient, right? And when it have gradient, the first thing that we should think of is Taylor expansions, okay? So, so we're gonna start it with gradient descent derivations. I don't see that many books do this, okay? So, but I think it's really, really essentials because we just cannot just simply take it for granted, right? Understanding intuition is important. Okay, so we start with, again, we consider F in the generic setting now in Rn to R. All right, so we're gonna Taylor expansion when we Taylor remainder theorem again. Right, at for F X J. So remember that we are at the current iteration. Remember that we have, okay, let me call J here. Okay, sorry. Let to be make sure that we have the same notation. Let me go up to here, pseudo algorithm here, J, I'm sorry, J equal to 0, Xj, then J. We update Xj plus 1. Okay, so we are at Xj right now, right? And J can be 0. And we're going to perturb, be perturbed a little bit away from Xj. Right, for where delta, we can take some positive number and P is any, right? Is any is in Rn with perturb, right? We add Xj right now. When we move away a little bit of Xj's, so we have F of Xj plus delta of P, right? By Taylor. By the way, deriving the Taylor expansion is also very interesting, right? We can do this actually constructively, but again, this is not, there's a certain thing that we cannot go through in detail, but it's actually itself is very nice. And I encourage you to do that. So if you expand this into second order terms around Xj, so this is the first order term delta P dot, right? P transpose or P dot. Right? If you familiar with the if you want to prepare the matrix notation, this is nothing more than the vector P transpose times the gradient vector X J. Okay, but yeah, we're gonna use both of them interchangeably. All right, and then we have the second order term, of course, right? That is delta square over 2. Let me rewrite it. It's a little bit ugly. And then P transpose the Hessians of F at Xj, and then P, right? Plus dot 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 dot. Okay. Okay, now we assume. Okay, we're going to assume that we assume that delta is sufficiently small, right, such that f of xj, the perturb, the evaluation of f at perturbed position is approximately given by the first two terms. Right? When this is sufficiently small, then P transpose undergrad student, a couple of you here. So did you take linear algebra before? Are you okay with that? Okay, good. So if not, let me know, okay? So P transpose have greater than F, so approximately like that, okay? So, okay, so remember the goal. The goal is to get to Fx star. And remember the definition of Fx star is what? Is the smallest, right? X star is the smallest locally, right? So when you start with some iteration of any point, for sure, right? F of xj here should be higher than fx star, right? If fx star is the minimizer, then f of xj must be lower, right? Unless we are on the minimizer, which is rare, right? So now we are given currently we are at fx. I'm sorry. We are currently at fxj right now, right? Or xj right now. We're going to move. So where should we move? To the better point. Remember that we need to update, right? And this is how we're going to move. We're going to move a little bit here. But the question is, what is the goal of moving? Of course, we want to move downhill. Everybody agree with me on that? Because we're going to want to move to a minimizers. So we want to go to a new place such that f of the new place must be smaller than f of the current place. That's intuition. Everybody agree? Okay, so if you agree with that, then we want, right? We want, or we wish, we want to go downhill, right? Downhill to f of towards f of x star. Of course, we don't know where x star is, right? Okay, so so one way is that now let us be very greedy, right? Let us be greedy by by solving this problem. F of xj plus delta p minus f of xj. And if I want to go downhill, right, I want to go as steep as possible, then of course I want, right? Because we are human, we always do optimization all the time. So today you wanted to go to NDU in the shortest path to minimize your time, right? Or if you take the train, you want to take the path or take the public transportation, you want to take the minimize the cost, right? As a student, I was a student before. I want to go to the path that take minimum amount of my money, right? So we do optimization on the time. So here we go. We're going to go downhill, right? Of course, we are human. We are very greedy. We want to minimize this, right? Remember that this, right? By design, by what we wish is that this is smaller than this. We want to go downhill. So this minus this, right? Because I move this to the right, left-hand side here. This minus this is negative. Right, so we want to minimize that. We want to go as fast as possible, as much as possible. So we want to minimize this. Okay, so we want to minimize this. We want to find the directions where we can go as fast as possible, right? P in N. Of course, right? Of course, this problem is approximate. Okay, so this is approximate equal side, approximate side vertically approximate because, right? This minus this is equal to that, right? So it's approximately by minimizing on the directions of delta P transpose gradient of F at xj. Everybody so far so good? So it's still, it's very intuitive, right? We haven't done any math or difficult mathematics or anything yet. Okay, so now, of course, right, this is equivalent to, because delta is positive, so this is equivalent to minimizations of P in R and P transpose gradient of F. And remember, right, P is what we don't know. Okay, actually it's good. It's good to remind us here. Remember here, right? Notice P is unknown, but gradient of F is known, right? Because we are at these locations, xj, so this is known. The only thing that we don't know is this. Okay, so we actually solving a very simple optimization problem now, right? Want to minimize this. And let me actually write it down. What is actually you can guess here. What is smallest? What's P such that this is smallest? What's P? Yes. So I'm sorry. The norm P is 1. Oh, okay, good. You need to do well. Yeah. We don't read that yet. Yeah, good. You're gonna see in a second. Yeah, we not yet, but yeah, let get that in a second. Okay, so by looking at this very simple thing here, right? What P should I choose? What P should I choose? Such that this is as small as possible. Of course, you're right. P cannot be an arbitrary in that sense, but at least can you actually looking at this and tell us what is P, the vector P, such that this is small or smallest? What is it? Recall. I mean, I'm still waiting for you, but I'm gonna write first. Recall. Any idea? Let me be again. Let me write this. Remember, this is a number. By the way, this is a number, right? This is a numbers. If I take the absolute of that, I know that this is less than or equal to what? That's a famous inequality that everybody knows. All of you know, even undergrad students. What is the inequality for the product of two things? Cauchy-Schwarz inequality, very good, right? So this is less than or equal to the norm of P, norm of the gradient of F. Very good. Thank you. Right, we know this is what we call the Cauchy-Schwarz inequality. So we see that, we use very simple techniques here, simple knowledge in mathematics here, not any advanced at all. Okay, so for this is equivalent to, right? This is equivalent to P transpose xj greater than or equal to a negative of P less than or equal to P, right? This is a simple thing everybody know. Everybody okay with that? I just simply replace the absolute values by double inequality. And you see, right? Ignoring the scale, right? This our classmate here is saying something good, right? He said ignoring the scaling. He said this guy is in between these two, right? And remember that one is actually negative. Remember, right? Our goal is to make this as negative as possible. That means we want to make this as negative as possible, right? That means we want to make this as negative as possible. That means, right? We should choose P's so that we attain this side, not the other side. Everybody see that? So the best P is the one proportionally, right? The one, and this is what we also know about Cauchy-Schwarz inequality. The equality happens, right? The equality happens, of course, right? We want By looking at that, we immediately see that, oh, we want P such that such that such that is equal to, right? We want the second inequality to happen, and that means P is equal to what? I'm waiting for you. That means P is equal to what in order for this equality to happen? So of course, right? We know for Cauchy-Schwarz inequality to attend, then these two need to be related. In this particular, what is the relationship between P and the gradient of F, such that the inequality not only happen, but it happened on this side, not the other one, not this side. What's the P? Say it again. So P is that a gradient like this? Is that what you mean? Close, almost correct. Hmm? Negative, right? Because if the P is equal to a gradient, so if P is equal to a gradient, everybody see, right? If P is equal to the gradients, then this will become gradient transpose times gradient, which is exactly equal to this, right? But without negative sign. Are you okay? Yeah. That's right. That's right. So equal to gradient in the opposite direction. Very good. Very good. Right. So of course you can have a scale. Okay. So the true thing is that P is equal to some, right? For some, just proportional is enough. But but what in practice, right? In practice, we don't. In practice, we take P is equal to the negative of gradient. Okay. So everybody, we have a. Let me actually recap what we did. So let us recap what we did, right? This is important, right? This is the whole thing that I want to share with you. In this third part is gradient descent. What we want is that we want to go to the minimizer, right? That means we're going to go downhill as fast as possible. We want to go downhill as fast as possible. And we start with the gradient. We start with the Taylor expansions. We ignore the second order terms. Right? We only keep the first order term. If we choose delta to be very small, right? That's justifiable. And then we really want to go very downhill as fast as possible, right? That means remember that this must be smaller than this for us to go downhill, right? I mean, you do hiking a lot. Taiwan is a beautiful landscape. In fact, one of the things that I will do in Taiwan to do hiking, right? So of course we do hiking, we do opposite, but we're gonna go downhill. We want to do as steep as possible to get to the bottom as fast as possible. So that means we minimize this. Minimize this is the same as minimize this because this is equal, right? Very simple, everybody, right? Then delta is actually greater than zero. We remove it, so we minimize this. And as soon as you see this Cauchy-Schwarz inequality come into picture immediately, right? And if you notice that Cauchy-Schwarz, then we say, oh yeah, because we want to go downhill. So this is the one that we should take, right? This side, not the other sides. And therefore P need to be proportional to the negative of the gradient of the functions. And in practice, we don't care about this, right? We just take P is equal to the negative of gradient. Thus, right? Thus, we conclude in summary. So we have derived gradient descent approach everybody. So summary, if we take P is equal to negative of gradient of F at the current point, or equivalently xj plus 1, or if we update xj this way, right, minus delta gradient, right? P is now minus of xj. Then we know we go downhill towards a minimizer. Okay, so we typically, right, we typically in optimization class, and typically this is what we typically taught, right? Oh, gradient vector is pointing upward or downward, uphill or downhill. The gradient vector pointing to the direction where the function is higher or lower. The gradient vector, which one? The gradient vector pointing to higher value of f or lower value of f. Higher. Okay, so this is how we typically taught. The gradient vectors is always pointing to a higher value of the functions, right? So if we want to go to the minimum, it's meaningful to go to the opposite directions. That's typically that we do, and that's the introduction of the gradient descent. We should go to the opposite direction of the gradient. But what we show here is that we derive it, right? By just very intuitions. We want the desire to go downhill, okay? So we just derive it. All right. So we actually are done with that, right? So let me actually write down the gradient descent algorithms, and then we are done with the gradient descent methods. So again, we are given x 0 and a tolerance f. I'm sorry, tau. That's a non-negative, and then we start with j equal to 0, and while the gradients of f at xj, the norm is greater than tau, which is not to the level that we want, we're going to update. We're going to update by what? Now we know xj plus 1 is equal to xj minus delta gradient of f. So you go in that same direction, and we go to the opposite direction of the gradient. That's why I call it gradient descent, right? Yeah, so this is of course how to pick. This is the interesting issue, how to pick delta. But let's say we know, right? Let's say we know, and then we just simply j is equal to j plus 1, and then n, and wow. Okay, so you see that, everybody, the gradient descent method, very simple, very simple, very simple. If you want to see it graphically, if we want to see it graphically in 1D at least, we're gonna do 1D visualizations. This is x, this is f, and let's say this is our function fx, right? And then we start from, let's say at xj, we are here, and this is xj, we are here. What we do is that the gradient vectors, right, in this case is the df, right, df dx is pointing in this directions. You see df dx, and negative of df dx is in this directions. See, negative of df dx, right, at xj, of course, at xj, right? So we go down here, we go a little bit, we go downhill a little bit, we get to this point, xj plus 1, and then we repeat. Everybody see that? And then we do it again. And then we get to a new point, and then we go again, right? And then we get to the, and eventually we get to a minimum. That's graphically how rate and descent works, and we should derive it. All right, how to pick delta, right? That's the question. I want to, we're not gonna spend time doing that, okay? So I'm gonna just mention here one popular way, one way to pick good delta is by backtracking. And I'm going to invite you to read in the lecture notes or Google. Okay, so the backtracking idea, at least I should tell you, backtracking idea is very easy. You do with step delta equal to 1 every time. Every iteration we start delta equal to 1, and if you go uphill, you cut in half and you redo it until it's good. Okay, so you start with some greedy and then you backtrack until you go downhill. The reason is that why do we do that, right? Because if you do step 1, you can go on the way here, right? And you may go to a higher value. Everybody see that? Because this method by definition is a local method. Gradient is a local information, right? So locally, we know that we go downhill. But if you take a large enough step, you may go uphill. So that's why we have to backtrack. Any question? Any questions so far? Okay. If not, then we move on. By the way, in Taiwan, do we have a habit of doing taking nap in the afternoon or after lunch? Do we? Elementary school? Oh, okay, okay. But how about like high school or maybe even undergraduate or graduate? Do you take nap? Do people take nap? Right. Yeah. I know this is 1 to 2 is not an ideal time. Very, very sleepy. I know. Some of you look very sleepy. Maybe you need some coffee or tea for the afternoon time. All right. So we're gonna move on. Move on. Okay. So that's a backtracking. So okay. So now we need. This is important, everybody. This approach. This approach. This approach. If it's converge, we know, right? We know that it's going to converge to the minimizer. A minimizer. Why is that? Because of course, intuitively, we take step to downhill to a minimizer. That's what we design the algorithm for, right? But how do we know? Especially, right? If we know, let's suppose, right? Suppose question that we have, right? Let's take us, right? Take us to a minimizer. This is more on reconfirmation, right? And by design, that's what it does, right? But does it? So let's answer, right? Answer first answer. Suppose xj converges to x, let me call x tutor. Suppose that the sequence that we generate, right? You see that we run this algorithm, we generate a sequence x0, x1, x2, so on and so forth, right? Suppose that sequence converges to an x tutor. Actually, yeah, x tutor, right? Suppose in particular, right? And then we show then x tutor is a minimizer. Indeed. Remember that we have this, right? Our iteration is like this. Okay, so if I take to the limit, if I take passing to the limit, right? Take the limit, passing to the limit, then j go to infinity. Take j go to infinities. Then what does the left-hand side converges to? Everybody, can somebody tell me? What's the left-hand side converge to? By our assumptions. By our assumption, what does the left-hand side converge to? Obvious. I'm not asking difficult questions. X tutor, that's correct. How about the first term in the left hand, the right hand side? What does this term go to? Hmm? X tutor 2, right? Because if the sequence converges, is j go to infinity, then whether j or j plus 1, both go to infinity. So this is x tutor 2. Nice. How about the last term? The gradient of f xj, what does it approach? What does it approach? How do we know? No, we don't know. We don't know. But we know this. Everybody agree with me on that? So we know that by many mathematicians here, math student here. Let me ask you a question. Why, under which condition, the gradient of f at xj converges to the gradient of f x tutor j? X tutor, what is the condition? Exactly, right? The gradient of f must be continuous, which we assume. We assume that our function is twice differentiable. In particular, this is continuous functions, right? If xj converges to x tutor, then the gradient of xj must be converged to x tutor j. Right? So this is just the last term is by continuity, right? So this is by continuity. Very good. Very good. Okay, that's actually nice. Now you see, right? This implies that the gradient of f. Now this is your guess, right? So now simply cancel x2 to both sides and divide by delta. I get this. So indeed, if the sequence converge, it must converge to a minimizers, right? So it's meaningful, right? By a very simple writing here. All right. All right. So, but of course, if we assume it converges, right? If we assume that the sequence converges, then we know that it's become a minimizer. And by the way, how do we know that x2 though is the minimizer? Because we can only conclude that the gradient of x2 though is equal to 0, which could be a or a saddle point. If many of you take optimization method before, right? X2 though satisfy this can be minimizer, maximizer, or saddle point. How do we know this is a minimizer? Because remember that by our desire, we choose delta. Remember backtracking that I mentioned. We go downhill. We go downhill, right? If we go downhill and we converge, we must be converged to our lowest point, which is a minimizers. Everybody see that? So now make connection with our theory before. Remember that the theory sufficient condition. The sufficient condition require what? Require that the gradient to be 0 and the Hessian need to be positive definite. Remember that's a theory. But we don't have Hessian here. So actually we've replaced the Hessian positive with downhill conditions. Each time we go downhill. And when we converge, we must converge to a minimizer. So we satisfy this, and x tutor must be a minimizer by constructions. Right? So we don't need the Hessian condition. So that's why gradient descent approach, right? If you go to gradient descent, and if you do backtracking, right, in particular, then we are sure that when it converges to a minimizer. Okay, sounds good. All right, but we still haven't answered the question. Answer in the correct manner. Yes, in these answers, we actually assume that is converge. So the sequence converge, right? So the second answers is the conversions, right? More rigorous answers is next. You know, I just show you here. Actually, I'm sorry. I should write what I just said as well. So I should say that. So we know and we know for sure that x tutor vector is a minimizer because each step, right? Because each step we go downhill, right? And when we converge, when we converge, we know that we are at a minimizer. Okay, so that's the now we have second answers, right? Next. An answer, the next one is a second answer is next. Is next. Oh, let's see, ugly. Okay, so conversion. We're gonna look at now conversion of the gradient descent. And by the way, every student or everybody here, I'm trying to this. I'm trying to provide you the background, right? Hopefully, enough rigorous and solid background for you to actually not only use machine learning but understand what behind the scene. Okay, so if you come here for learning practical machine learning method, then this class is not for you. Right? This class is to provide you the foundations, right? The foundation of machine learning, deep learning in particular, and on the important subject behind the scene. So if you really just say, oh, just teach me how to use convolutional neural network, if you teach me how to do reinforcement learning, thing like that, this is not this class is about. Okay, this class you see when you do training, you choose SGD, or you choose an Adam solver, right? Or you choose any method. You know what happened behind the scene because you now have the not your solid background what it does behind the scene. Okay, so if that is what you're looking for, then this is a class for you. But if that is not, then this class is not for you. Okay, that I just want to make sure that we understand very clearly. I'm trying to provide you the foundations of the machine learning method, right? In particular, deep learning. All right. So conversions is a little bit more mathematical, but we're gonna cover this a little bit and then tomorrow as well. Actually, we only cover 50 minutes, right? We don't not gonna. I think we should take break. So is it normal here? We do 50 minutes, 50, right? Yeah. Okay, 50 minutes at a time. So then I think it's a good time to stop as well. Okay. So tomorrow we're gonna spend maybe half an hour or so to finish the conversion of the gradient, and then we jump to a completely separate subject, probability, and then we see that how they play together later. Okay, when we look at understanding deep learning, training deep learning, how deep learning behaves, and so on and so forth. Okay, everybody, sounds good? I see you tomorrow. Bye now. Thanks for being here.